Okay, momentum. Here's what we got. When Newton came up with his second law, it actually didn't look like that. F is ma. What it looked like is, because we know the definition of acceleration is a change in velocity over some change in time, what he actually came up with was this for a second law. This he gave a name, this mass times velocity, and he called it a quantity of motion. And this is quite an important concept. It was quite a breakthrough at the time. All right, we have another word for this. Quantity of motion, mass times velocity. We call it momentum. Momentum's given the letter P. Okay, so that is momentum. Look at a couple of examples. Where am I? I guess we'll do this first. Impulse is known as the change in the momentum. Okay, so because momentum is P, our sign for change in means delta P. And because P is mv, we write change in mv. Now it's not the mass that's going to change here, but what can change is the velocity. So we actually write this formula like this. Okay, so what is an impulse? If something is moving at some velocity, and of course it has some mass, how much force do we need to put into this thing over some period of time to get it to stop? That's what we call the impulse. The change in the momentum required for it to go at some speed to stop. Okay, maybe we got some speed and it just changes speed. Maybe we have an initial speed and maybe we have some final speed that's not zero. Remember, the change in velocity is final minus initial. So we can work that in there, and it'll ask what is the impulse if something goes from, I don't know, 15 meters a second, which goes here, to 25 meters a second. What is the impulse required to make that change in the momentum? Okay, you just put the numbers in there and you solve it. So, because F is mv over t, I could, let's write it, okay, multiply both sides by t and bring the t up here. And that's how the formula looks like this, okay, which is on the back of your book. And the other formula on the back of your book is simply this. Okay, so because this is the change in momentum and this is equal to this, then this is also the change in momentum. Okay, so it's two ways to say it. And of course, change in momentum is called impulse. So some force over some period of time will change the speed. Maybe it'll make it slow down, maybe it'll make it speed up. Okay, that's the concept of momentum and impulse. Units, of course, where am I? Right here. Units, well, it's mass times velocity. You know, mass is kilograms. You know, velocity is meters a second. So that's kilogram meters per second. But also, units of momentum could be forces newtons and time seconds. It could be Newton seconds as well. Okay? I'm not going to drill you on the units on a test. We just need to come up with these numbers. Okay, so this is as simple as it gets. What's the momentum of that football player running with that speed? Momentum is a product of mass and velocity. 112 times 3.6 which is 403. Let's just round it to the whole. Okay, units, kilograms, meters per second. Impulse. What impulse must a tackler give to the football player to bring him to a stop? Well, what is impulse? Impulse is the change in momentum. A stop means my final velocity is 0. Initially, it was 3.6. So change in momentum is impulse, which is mass times change in velocity, which is 112. 0 minus 3.6 is final minus initial. That's the change in V. And what we get is exactly what we had to start with. Okay, only it's a negative because it's in the opposite direction. If this guy is running that way, how much force over some time do I need to put on this to bring him to a stop? Okay, exactly the same amount in the opposite direction. So you can think of the concept or just use the formula and work it out. If the tackle was completed in 0.8 seconds, what force did the tackler exert on the other player? This is impulse, okay? Change in momentum. So, do I have this? Yes, I do. I just answered it. And what do I do with this time? I want to find the force. Well, divide both sides by t. And the force is negative 403 divided by 0.8. Force, of course, is in newtons. Put that in your calculator, and you should get 504, and it's negative. Because, of course, that force is in the opposite direction as this runner was going initially. If I took that as positive, then that direction's got to be negative. Okay? So, I just answered that question already. Next concept, a little trickier, is this notion of law of conservation of momentum. Momentum is conserved. Okay, we've noticed this long before we had electricity. Total momentum in some system is constant. The only thing we're going to do when we talk about our system is have maybe a maximum of 2 items. Okay, well, maybe 3. Okay, so a closed system. All we need to know is whatever momentum you had before, that's how much momentum you're going to have after. After or before what? Some situation. It might be a collision, okay? It might be an explosion, but this is the concept. The momentum before is equal to the momentum after. It's not created, it's not destroyed. What you started with is what you end up with. Okay, so let's look at this example. Got a couple more. A railway car. I like pictures. I'll do it right here. Okay, there's my railway car on a railway. It has a mass 6,000 kilograms, and it's coasting along. Coasting is a word implying there's no acceleration, with a velocity of 5.5 meters a second. Suddenly, a 3,000 kilogram, 3 times 10 to the 3, load of sulfur, there it is dumped into the car. So we can assume, even though it doesn't imply it, that this load of sulfur, since it's dumped into the car as the car goes under it, okay, after this sulfur is just going to land in the car. So what's the speed of the sulfur? Nothing. All right, so my picture here, this is a line which divides before this collision of the car and the sulfur and after. Okay, So momentum before equals momentum after. That's the principle by which we do this question. What's the momentum before? I have momentum of the car. Momentum is m times v. And momentum of this sulfur before, but because the momentum is a product of the mass times the velocity, and the velocity is 0, then momentum of this sulfur is 0. After equals, what do I have? I have this car, which is 6,000 kilograms. I have the sulfur, which is 3,000 kilograms. And they're joined together. Okay, this sulfur was dumped into the car. So let's treat this as just one mass. Times some velocity is what I don't know. That's what I'm trying to solve for. All right, so 6,000 times 5.5 is what? Now let's just do it. Hard to read that. 6,000 times 5.5, that's the momentum before the collision. 33,000 kilograms meters a second. And after, I have this mass, but I don't know what speed it's traveling with. So I just solve this for v. One equation, one variable. I can solve this. v is that divided by 9,000. What would we guess? Do we think the speed's going to be greater than 5.5, or should it be less? It should be less. And it is. 3.7 meters a second. Okay? Momentum before is momentum after. They've solved it here. Feel free to read it and do it their way. Okay. Two identical air track gliders. Each has a mass of 100 grams. First, I want to make that kilograms. Okay, everything needs to be in kilograms, meters per second, or you're going to get the wrong answer. They're sitting on an air track. All right, so here's my air track. I got two of them. All right, each one has a mass of 0.1. I'm not even going to put units here. One glider's at rest. The other glider is moving toward it at a velocity. Well, it doesn't give me a number, so that's probably what I got to solve for here. Okay? When they collide. Okay, so this is after. They're going to collide and stick together. So let's stick them together. They move off at 2 meters a second. I don't know what direction, okay, but it's probably the same direction as this one, but it might not be. Maybe this one has a negative velocity. I'm not sure. If this one I'm taking as negative and that's positive, does that make any sense? No, it doesn't, right? So it's got to be going this way. And I do know the mass. It's 0.1 and 0.1 or 0.2. Okay? Again, conservation of momentum. Momentum before is momentum after. What momentum do I have before? I have 0.1 times v. What's the momentum of this one? Nothing, because there's no speed. Equals, what's the momentum after? Mass times velocity. Solve this for v. Divide both sides by 0.1. And v is 0.2 times 2 divided by 0.1, 4 meters a second. I will leave that one for you guys. Just watch. They're not asking for the velocity or a mass, they're asking for the momentum. Okay? So if you find v, you got to times it by m. Let's look at this guy. A ball rolls at a velocity of 3.5 towards this ball at rest. Okay, 3.5 meters a second, 5 kilograms, and I know it's at rest, the velocity 0. They collide. Okay, after they move off at a velocity of 2.5. They move off. So that means that's the velocity for both of them. Doesn't necessarily say they're stuck together, but you can think of it like that. And what's the mass of the moving ball? I don't know what this is. Okay, so it's an unknown here before, and still an unknown here after. I know the mass of that guy. That's 5 kilograms. Momentum before. Once again, this thing has no momentum. I know the momentum of this is 3.5 times m. Okay, mv, that's momentum, equals 2.5 m is the momentum of that one. And I have the momentum of this one, 2.5 times 5. So I got to solve this thing for m. I got m's here. I got m's here. Let's bring all the m's to the left. Subtract that. Don't divide it. It's plus 2.5 m, right? The opposite of that is subtract. 3.5 take away 2.5. That's 1 m. Or just m is, the only thing left I got here is 5 2.5s. $2.50. You get that 5 times, you got $12.50. It's a mass, so that's kilograms. Okay. One more. And actually I need that space. Well, let's throw that up there. All right. This is a little different. Same principle, momentum before is momentum after, but it's like an explosion question, okay? A 4 kilogram gun recoils. Do you guys know what that term means, recoil? If you've shot a gun, you know how it feels. The more powerful the gun, the more you feel it. After firing a 0.05 kilogram bullet, what is the speed of the bullet? And this is actually how you can determine the speed of a bullet, because I don't believe radar detectors pick these up. They're too small and they go too fast. At least the old ones didn't. They might be able to now. But you can use physics to actually find this out. Okay, so here's my crude little gun. I don't know, got a sight. I was going the wrong direction, so I redrew it the other direction. There's my gun. Inside of it, I got a bullet. And when you pull the hammer, it creates a little explosion and blasts the bullet out of the gun. So this is before it shoots. After it shoots, we have the gun, which recoils, and we have the bullet, which of course is shooting in the opposite direction of the gun. That's what I want to know, the speed of the bullet. I know that's 0.05 kilograms. I know this is 4 kilograms. Okay. So, what is the momentum before? Assuming we're not walking with this gun, we're standing still. It's 0. The gun's not moving, the bullet's not moving. Before we fire, the momentum is 0. Momentum after, I have 4 kilograms times 4 meters a second, and I have the bullet, 0.05 kilograms times the speed, I don't know. This is our equation. 0 is 16 plus 0.05 V. How do I solve this for V? Get rid of the 16. Divide by, well, it's negative. Divide by 0.05, and my velocity of the bullet should look like it kind of makes sense. 320 meters a second. And that looks reasonable to me. Okay. Oh, and it's negative, isn't it? So again, I don't really care about the negative part. All this means is the bullet is going in the opposite direction that the gun is. Okay? If I took the gun as negative, if that direction was negative, then this direction would be positive. It's just convention's sake. Okay? And if this was a Cartesian coordinate, that's actually how I should have done it. But it doesn't matter. I don't care. All I want is the magnitude. All right? We know it's in the opposite direction as the gun. This is the only thing I care about, 320. All right? So one other thing. That's the concept. You don't really have to do this part. The other way to think about it is, you know the momentum before it fires is 0. So after, this has got to equal that. Okay? The momentum of the gun has got to equal the momentum of the bullet. Because before it had no momentum. So these have to equal nothing. Okay? One of them's got to be a negative. It doesn't really matter where you put it. So you can just start with that. The momentum of the gun is 4 kilograms times 4 meters a second. The momentum of the bullet, I know the mass. I just got to solve for the velocity. Okay? It doesn't matter which kind of way you think about it. But an explosion question, that's what's going to happen. Okay? So, questions you're going to do are page 125, number 2. That's the one I skipped right above here. Page 126, 4 and 6, and page 129, 14, 15. And explosion questions I just have differently, so you can do them after or do them all in order here. I'll leave it up to you. 126 number 3 and 129 number 13.